Okay, we're going to go ahead and solve the second free response question. This one they say is from Unit 2, so that's involving more forces and things like that. So let's have a look at the problem, and I'll get the blue pen out here. It says to read each question carefully, show your work for each part of the question. The parts in the question may not have equal weight, and they have a picture of what looks like an inclined plane with a mass on it, so I'm already thinking about my inclined plane stuff. The narrative says a block of mass m is placed on an inclined plane that makes an angle theta. What the hell is that? Interesting. With the horizontal as shown in the figure. The coefficients of static and kinetic friction between the block and the surface are mu s and mu k. Okay. Oh, that's one of my doggies. Got it. So I'm going to write that down up here. We do have friction. I'm going to put that underneath the plane just to remind me that friction is present. Express your answers in parts B and C in terms of, here we go, m, theta, mu s, mu k, and physical constants. Cut off physical constants. I don't think you need to include physical constants when you box this thing, but it is important. On the dot below, which represents the block, draw and label the forces. Okay, this is what we have to do. Draw and label the forces, not components that act on the block as it is at rest. Not components, that's important. Each force must be represented by a distinct arrow starting on and pointing away from the dot. The dashed line represents the direction of the incline. Okay, this is going to be simple. We know that there's going to be a normal force, and I'll label that N. We know that weight is going to pull straight down. I'll label that mg. And if those two forces were the only forces, this thing would slide. So we suspect that there's going to be some amount of friction. All of those arrows originate on the dot and go in a direction. They may not be exactly proportional to the size that they are, but this is what I would do. Now it says, please respond on a separate sheet of paper following the directions from your teacher. Yeah, okay, I did it right there. Sue me. Part B says derive an expression for the maximum value of theta. So we're going to be deriving an expression for the maximum value of theta for which the block will not slide down the incline. Now, is there any more to the question? Okay, good. So we have to find a maximum value of theta. Now, look, I think I can squeeze this into this area here, but that probably wouldn't be very useful. So let's go ahead and solve it right here on this thing. Blank sheet of paper. So we have our free body diagram, which I'm now going to draw with components. A normal force going this way, a frictional force going this way, a component of weight mg cos theta perpendicular to the plane, and a component of weight mg sine theta pulling down the plane. And at this point, we can figure out the maximum value of theta by figuring out the maximum value of f. You see, what's going to happen is we need f to be equal to mg sine theta. Now, f itself is mu static times the normal, and that's the maximum value of f. So that's when it's at the maximum theta. Remember that f is always less than or equal to mu static times the normal. So we're going to go to the extreme case where it's equal to mg sine theta. Okay, the normal force here is going to be exactly equal to mg cos theta, and that's going to equal mg sine theta. And so all the mg's cancel, the cosine under the sine, we get that mu s is going to equal tan theta, or theta is going to be the inverse tangent of mu s. And that would be an expression for what the maximum value of the angle could possibly be. Excellent. That should do pretty well for me. So let's see what we got here. Moving some papers around. We did that. We're on to part C. Now, part C has a little prompt. It says, assume the value of theta is greater than the value from part B. Okay, so we've exceeded the static coefficient. We're moving into a kinetic coefficient. Derive an expression for the acceleration of the block. All right, well, we can do that. Let's look at this picture again, and now we're going to say that this frictional force is, first of all, it's going to change to kinetic friction, and second of all, this force mg sine theta is going to be larger. So that means that the net force is going to equal the mass times the acceleration of the object, and in this case, the net force is going to be mg sine theta downwards minus friction upwards, and that's going to equal m times a. Well, skipping a step here, we put in mu k and the normal, which is mg cos theta. That hasn't changed, by the way. The up and down forces are still equal to each other. And this is going to equal m times a. And lo and behold, all the m's cancel. And we can factor out a g. So g times the quantity sine theta minus mu k cos theta on this side equals a. And we've done it through the magic of algebra. We have an expression for the acceleration. So we might have said up here, we might have said that mg sine theta minus friction equals 0, because that's the same thing. F net equals m times a. This is the net force in the down the plane direction, and it's going to be equal to 0 in this case. So I might put that up here just so that they know, but I think they will imply or infer, that's probably the right thing, infer that you're doing that when you set this equality right here. Okay, so we've got part C nailed. And then now part D, the incline is set with angle theta. Oh boy, this is going to be interesting. The incline is set with angle theta. The angle is slowly increasing until the block begins to slide. Okay, so somewhere between part B and C, after the block begins to slide, the angle is kept constant. So we are sliding, but the angle is being kept constant. Part I, until the block begins to slide, does the force of friction acting on the block increase, decrease, or remain the same as the angle increases? Okay, so the answer is to increase, okay? And the reason is, we said before, that the force of friction is always less than or equal to mu static times the normal. And as we tilt this thing up, two things are going on. First of all, mg sine theta is increasing. And therefore, that means that the friction must be increasing. So that's the justification. So I don't know if you would do it this way. I might use the word increasing instead of this arrow up. This is something I do with you guys in class. I don't know if the AP graders are hip with this thing, but this is what I would, this argument here is what I would do. If the block is sliding down the incline, does the force of friction acting on the block increase, decrease, or remain the same? Now, once it's sliding, then we have kinetic friction, which is an equality. So it stays the same. The force of friction is going to be mu k times mg cos theta, and all of these things are staying the same. All of these things are constant. So you would have to argue that that is true. Okay, now finally, it is determined that for this surface, the force of friction is proportional to the speed of the block according to this equation. Okay, that looks familiar. I've seen this before. This is our drag problem. This is where we get our differential equation and some other things out of this. So we know how this works. We could find a terminal velocity for this thing. We kind of know what things look like. And it says E, on the axis below, sketch the speed and acceleration as a function of time. Okay, this is something that you just should know, that the speed will start at 0 and it will increase, but the rate of increase will decrease. In other words, it's going to be one of these exponentials that turns over and becomes asymptotic to some terminal velocity. I don't think you have to label this as a terminal velocity, but points if you do. It has this shape because it is a 1 minus e to the minus something. We worked this all out. You should know that this is the velocity versus time curve for something that's undergoing drag, this kind of drag. What does the acceleration do? Well, remember, when we have drag, you jump out of the airplane. At first, you have a very large force down, then there's a retarding force, so that makes the overall force smaller, and then finally the forces become balanced and the acceleration is 0. So the acceleration is max, and then the acceleration is 0. So we should have something that decays down and becomes, I probably shouldn't have it touch the axis. It does become asymptotic to the axis right here, and there's probably 2 points for that. In fact, if I want to go through and give you the point breakdown, I did dig up the point breakdown for this particular problem. So let's have a look at the point breakdown. All right, here we go. So for the drawing here, there were 3 points, one for each of the forces, and any extraneous forces or components would cause you to lose away from that 3. For the deriving of the expression, this was worth 3 points. I don't have a sub breakdown on that. Part C, Deriving expression for the acceleration of the block. This was only worth 2 points. I assume because you already showed that you know Newton's second law from part B. Part D was worth 2 points, one for the increase, one for the explanation. That was DI, and DII is also worth 2 points, one for the remain the same, the other for an explanation. And finally, this was worth 3 points, one each for the shapes, and the other was for, I don't recall, maybe this one going asymptotically towards a maximum amount. So that would add up to your 15. So that's what you're up against on this problem. I will unlock this video at noon-ish, and so you can check your work. Thank you.